enthalpy. Enthalpy is basically a measurement of the energy associated with the chemical reaction. So in a chemical reaction, you're always breaking bonds and making new ones. So it's the amount of energy it takes to make and break bonds, and we measure that in form of heat, okay? So the energy associated in a reaction to make and break bonds in the form of heat, okay? You can have positive enthalpy, which we call endothermic. That's when you need heat for it to go. You absorb heat. And then exothermic, you release heat. Okay, so let's look at some examples of that. Sweat evaporating. Okay, look at this little note I wrote down here. If something becomes more gas-like, it's endothermic. Think about boiling water. Okay, you had to put heat into the water for it to boil, right? So that's endothermic because you need heat to boil. Okay, think about when something becomes more solid-like, it's exothermic. So think about ice again, or water. To become ice, you need to release heat, right? It needs to become cold. So if you're releasing heat, that's exothermic. So if we look at these examples here, sweat evaporating. So that evaporating means it's becoming a gas. So sweat needs to sweat will be endothermic, right? Because it needs heat to sweat. So this was endothermic. Water freezing, so it's becoming more solid-like. It needs to expel the heat so it can freeze, so that's exothermic. Wood burning, think about a fireplace. Heat's released, right? So that would be exothermic. You can also do stoichiometry. So if we're looking at this, we're looking at like a combustion usually, okay? So in this reaction here, this tells us for this reaction to occur, this much energy is released, okay? Negative 2,044 kilojoules of energy. So that's how much energy you get from that reaction. You can also look at it per mole, okay? So do you see that it took 1 mole of methane for this reaction to occur? So 1 mole of methane to get that much kilojoules, okay? But how many moles of oxygen did you need? Do you see here? 5. So it took 5 moles of oxygen to get that, okay? But what if you wanted to know per mole? So I have 5 of them, but what if I want to know how much energy per individual mole? Well, then I would just divide this number by 5, and I would get per mole, right? So that's sort of the conversion you can look. You can say how much energy per that individual mole. So let's look at an example of here what I'm talking about. So this says a home barbecue contains 13.2 kilograms of propane. Okay, so I have a propane tank, and this is how much propane I have, 13.2. And I want to calculate the amount of heat will then be released per mole of propane if I have that much propane, okay? So I have this propane tank here. Propane. And in here there's 13.2 grams of it, okay? I want to know how much energy released in RG released per mole of this tank. So basically, how much energy will this create? Okay, if I have this many, that was kilograms. Kilograms, how much energy will then be released per mole of propane? Okay, so if we look at the previous slide, we actually have the reaction for that. It says C3H8 plus 5O2 yields to 3CO2 plus 4H2O, H2O, and the delta H is negative 2,044 kilojoules. So this would have to be given to you, this whole equation and everything, and that was given to you in the previous slide. So we start here. We have 13 kilograms. So we have this many kilograms. So now how much heat will be released? Okay, that's a lot. Okay, and we want kilojoules. What we're trying to find, think about your units here, kilojoules per mole. We have grams, but we need to go to moles. But first we need to get kilojoules to grams. So kilograms at the bottom, grams at the top. For 1 kilogram, there are 1,000 grams. Okay? Now I could go from a gram to a mole, or anytime I'm going from a gram to a mole, I use molecular weight. Propane weighs 44, I just calculated that, grams per 1 mole. Okay, now I'm getting close, because now I'm in moles, but I want kilojoules per mole. So I can look at my chemical equation here. I know I can put moles here to cancel out. Do you see I have 1 mole of propane per, for this problem to get that many kilojoules? Kilojoules. So now I have my kilojoules per mole, which is what I wanted. So this is good. Now let's say I was looking at oxygen. Well, then that would have been 5 per 2044. Or if I was looking at CO2, that would be 3 per that, because there's 3 of them versus 1. Because this takes 1 mole or 1 molecule of this to create that many. But if I was looking at oxygen, it takes 5 of them, so I'd have to say, well, it takes 5. So let's multiply and divide this out. Okay, so we have 13.2 times 1,000 times 2,044. And let's divide that by 44. And we get 1613 200 kilojoules per mole. A lot. And, oops, sorry, that wasn't supposed to erase it. Negative. So do you see, when I have now this many, if I have 13.2 kilograms of this, I will now release 613,200 kilojoules per mole of it. Okay? So that's a lot. Anyway, so now it's saying, basically if I have that much propane, how much energy will I get? And this is the answer. So next we're going to look at how to actually calculate delta H. So it was given to you here, but how do they get this number? And I'm going to show you a pretty easy way.